I'm Patrick Taylor from NASA Langley Research Center, and I want to shift gears a little bit, and we'll talk about the Arctic. And so, what I want to tell you guys about today is that NASA has a key role with all of our Earth-observing satellites in trying to understand why the Arctic's changing, how fast it's changing, and what the future holds. So I want to tell you this story, and the story actually begins last month. I was driving home from work, and I came across some traffic. And so, like everybody does when you hit some traffic, right, I pulled up my iPhone, and I look at Google Maps, and I try to figure out where is this accident, and is there a way I can get around it, right? And so the map was full with red. It was red everywhere. Traffic, couldn't get around it. I just had to suck it up and be okay with the fact I'll be 10 minutes late for picking up my daughter at work. And so since I had time sitting in traffic, no texting and driving, just sitting around, I decided to try to figure out where this accident was. So it turns out it wasn't anywhere close to me. It turns out it was like 10 minutes or 10 miles away on the interstate. And so an accident on the interstate 10 miles away flooded the more local lanes of traffic where I normally drive to and from work, and then causing me to be late. So this is my little local metaphor for what's happening in the Arctic and why we need to care. So while this is a local example, these rapid changes that we're seeing in the Arctic have the ability to rapidly and unexpectedly kind of clog our local climate traffic lanes. So what happens in the Arctic certainly doesn't stay in the Arctic. These rapid changes that I'll talk about here in a second are like throwing a rock in a pond with these ripple effects that have a global reach. We start this one over. Okay. So we're at a different part of the animation, but what I want to talk about are these great satellites that NASA has, and they really enable us to understand the Arctic better than we have ever before. I like to think of the climate system a lot like a gigantic puzzle, where the different pieces of the puzzle are the plants, the animals, the ice, the ocean, the atmosphere, and of course you can't forget humans. And it turns out that no single satellite or country or mission is able to observe all those pieces of the puzzle by themselves. And so that's why we have so many satellites. And so over the last 30 years, so we've been, during the satellite era, roughly about the last 30 years, we've been watching the Arctic change and the planet change. So what you're looking at behind me, though, are the changes in temperature from the GISS temperature record since 1880. We've seen that in this time, the Earth has warmed by roughly about 1 degree Celsius, or in the order of 1.6 degrees Fahrenheit. Maybe more striking than that is that 16 of the last 17 years have been the warmest on record, where 2014 was the warmest on record, but then 2015 eclipsed that, and then 2016 eclipsed that. 2017 is not expected to be the eclipse last year, not expected to be the warmest on record, but it is expected to be amongst the warmest 3 years. So what you see here as we're moving forward, the areas that are in red are showing you places and times that are warmer than average. The blue areas are cooler than average. The base period for this is 1950 through 1980. As we get forward in time, you see that this red cap here develops on the top of the planet. And this is the rapid Arctic climate change that I was alluding to earlier. The Arctic is warmed twice as fast, at least twice as fast, as the rest of the planet. And so, making that observation, a couple questions come to mind. So why is the Arctic changing so fast, faster than anywhere else? And what are the impacts of those changes? So first of all, some of the impacts. It turns out that a warmer Arctic ends up being a less icy place. So first of all, here's some data from NASA GRACE instrument. It's one of the coolest missions that we have, I think. And you see the vectors over here on Greenland are showing you where the ice is flowing. The red colors here are showing you places where we've lost the most ice. So here's the average over the entire continent between May 2002 and 2016, August 2016. On average, we've lost about 281 gigatons per year. And I don't know if that number necessarily means something to everybody, but let me put it into perspective for you. That's the same amount of water that you could use to fill up more than 140 million Olympic-sized swimming pools each year. So it's quite a bit of water that Greenland is losing every year. In addition to the Greenland ice melt, we're losing, the sea ice is declining as well. So what you're looking at here are, this white area is September sea ice from 1979 through last year, through 2016. The yellow line is showing you the aerial average for each of those same years. to me, this image, this decline in Arctic sea ice that we've seen is one of the iconic images of rapid Arctic climate change. You'll see that we've lost, on average, about 300 million, sorry, not 300 million, 3 million square kilometers of Arctic sea ice on average in this time period. That's the same as the land area of Alaska, Texas, California, and Montana combined. So it's quite a bit. It's about 50% of the aerial extent that we had in 1979. And so for me, when I put that statistic together, I didn't realize how big Alaska was. So Alaska is actually 3 times the size of Texas. So this decline in sea ice that we've seen is roughly about just more than 4 times the size, the area of Texas that we've lost. So it's not just the sea ice aerial extent that's changing, but we've seen a lot of changes in the age as well. And the reason why we care about sea ice age is because it's a direct diagnostic. It tells you about how thick the sea ice is. And so when I picked this animation, I wanted to put the monthly animation. So what you're looking at is sea ice age from 1984 through present, but each month in between. And so why I think it's so awesome is because you see the dynamic nature of the sea ice. You can see it kind of the oldest sea ice, which is shown here in white, building up here north of Greenland, flowing over this way towards Alaska, and then this huge export via the Fram Strait. So it's a pretty dynamic system. It's more than just a surface energy budget. It's more than calculating fluxes that determines this, determines how the sea ice changes. But the dynamics and the interplay between the atmosphere, the ocean, and the sea ice is really, really important. And I think that this really shows that. So now we're in 2001, and what we're seeing here is that slowly in time, those white colors are becoming fewer and fewer, and you're seeing more and more gray colors, light gray colors come. So those gray colors are the younger sea ice, 1 to 2 year old sea ice. And so in the beginning of this, the oldest sea ice, this very bright white sea ice, was accounted for about 20% of the total sea ice cover. When we get to 2016 here, you'll notice that it only counts for roughly about 3% of the total sea ice cover. And so, again, why we care is because this older sea ice is much, much thicker. Okay, so the first year sea ice gets to, at best, like around 2 meters tall. And I'm about 2 meters tall. Okay, so I'm first year sea ice, or so, 1 to 2 year sea ice. The oldest sea ice there that's older than 4 years, the multi-year ice can be up to 4 meters tall. So picture me standing on top of my head. And so that's about 4 meters tall. And so it takes a lot more energy to melt that sea ice than it does to melt the younger sea ice. And so what we're looking like we're in store for is thinner, younger sea ice is more vulnerable than to melt. So one key question then is, do we expect these changes that we're seeing right now to continue? And if you ask climate models, they will unequivocally tell you yes. And so what you're looking at here is my spaghetti plot, where each different line here represents a different climate model. And the y-axis over here is normalized temperature. So what I've done is taken each of these models and divided by the total global warming. And so if you see this latitude region, so the Arctic is over here on this side. And so any latitude region that has this 1, that means it warms the same amount as the globe. So what you'll see here, you can think of this kind of as an amplification factor, I guess. So you see that if you ask the models how much the Arctic will warm, it's going to warm anywhere from 1.5 times to almost 3.5 times more than the globe does. And so if you take the IPCC number, about 3 Kelvin increase in temperature for double CO2, that's telling you that the Arctic can warm anywhere from 3.5 or 4.5 to more than 10 Kelvin. And this is projections by 2080. So we certainly think that that the Arctic is going to continue warming at this rate. And in addition, you see the spread between all these lines is much, much larger in the Arctic than anywhere else. So the question is, okay, so we know that these changes are going to continue. So why are they happening? And so this was a question, actually, like what's driving rapid Arctic climate change? This is a question that I think we thought we knew the answer to, but with the use of satellite data and models, I think we're learning that maybe we don't know the answer as well as we thought we did. But the original answer is the ice albedo feedback. So in the Arctic, we have a lot of sea ice. It's bright, it's white. It reflects a lot of solar radiation. So as we warm the Arctic, though, and we're uncovering this darker sea ice underneath, what we get is that a lower albedo, so more solar radiation is being absorbed in the ocean, heating the surface, then melting back more sea ice. So then we see this as this amplifying feedback loop that's operating. And so this is a local feedback. So it seems pretty cut and dry. This seems like something that's operating. And we have some observational data that shows us that, yes, this is happening in the Arctic. But it turns out, and I'll show you the temperature changes that we've seen, but it turns out there are some arguments that say that maybe this isn't the only mechanism that's operating to drive these changes in the Arctic. So what you're looking at here is trends in MERA2, so NASA's reanalysis data set. The red colors here are showing you places that have warmed more. So this is the trend in temperature in Kelvin per decade since 1979. The y-axis here is height. So this is the surface right here. This line on the bottom is showing you what the surface warming is, and then 100 millibars, so we're going higher in the atmosphere. And so what we call this is our bottom-heavy warming profile, the fact that the Arctic is warming much faster at the surface than it is aloft. And so for a while, this was used as evidence to say, oh, look, we see this surface warming that's happening. It's mostly a surface-based warming, and so that means the ice albedo feedback is the most dominant reason that the Arctic is warming so fast. But we're not quite sure. There's a second mechanism. Let's see. There's a second mechanism that we call the remote. So that was a local mechanism, meaning melt sea ice, warms the Arctic more. Well, what about the rest of the globe? So it turns out that there's a remote forcing mechanism, which says that the changes, what's happening in the tropics or in mid-latitudes could actually be influencing the Arctic. And so, first of all, I just love showing this animation because it really it just shows how dynamic and amazing the atmosphere is and how good the models are at simulating it, how realistic they are. This is the nature run from GEOS-5, NASA's atmosphere model, and it really, so what you see here, you have these mid-latitude cyclones. So here's an example of the remote forcing mechanism, getting back to the Arctic. And that says that if changes in heat and moisture transport from tropics or mid-latitudes into the Arctic could actually be driving the Arctic to warm faster. And so how I would show this on here is every once in a while, these episodic moisture intrusions where you see these cyclones moving around and they get advected and they move right into the Arctic. And they bring a whole lot of heat and moisture with them. And so then they change the surface energy balance of the Arctic. They increase downwelling longer radiation and then help amplify the warming. And so that's the second mechanism, the remote forcing mechanism for driving Arctic changes. Right. So wrapping this up, so I would say, where do we stand right now in terms of understanding what's driving the Arctic? And I say we don't really have an answer right now, but it may not actually matter which of those mechanisms that I described are really more important. Because in a recent study, it actually showed that if you want to get really rapid Arctic climate change, you actually need both of those mechanisms to work together. Okay, the transport of energy and water vapor into the Arctic plus the sea ice, and it seems that we have that we're seeing some of that right now. And NASA satellite data is going to be very critical in understanding that coupling between the two. So I started by saying about how what happens in the Arctic doesn't stay in the Arctic, and how our whole climate system is really, really connected. And so here's an animation of what is Earth's circulatory system. And I do like thinking of it that way. So like the circulatory system in our body, our heart pumps blood, transferring nutrients and oxygen that we need to live from our head to our toes, and making sure our entire body is connected. The thermohaline circulation does a similar thing for Earth's climate system. So the density gradients driven by temperature and salinity are driving these currents that are transferring water and energy from equator to pole and back again, which really makes sure that our climate system is connected. And so with that, I think I'd like to close by saying that, again, what happens in the Arctic doesn't stay in the Arctic, and I think that that's a message that we as scientists need to make sure we convey. Because one of the biggest questions that I get when I go give public lectures on this stuff, on Arctic climate changes, is why does Arctic climate change matter to me? It's so far away. How can it impact me? But it turns out that every once in a while, even unexpectedly, changes that are happening really far away can clog up my atmospheric traffic lanes. So with that, thanks.